so we'll do some that way. Let's do, oh my God, where did the time go? Let's do the pendulum. Let's see. Wow, it all went here. That's what. Okay. We're going to think about the big bowling ball mass here. And we'll do some problems. Some will be elementary, some will be difficult. We'll start with this one that's slightly elementary. So let's how to use it. Use E mech equals a constant. All right? So we have a pendulum, a large pendulum. The bowling ball. Released from H. You'll see what that means when I draw it. From H. And how fast at bottom. Okay, these are non-verbose versions. How fast is it going at the bottom of its swing, right? So you've got the bowling ball like this, and it's going to swing down to, here, and then it's going to come back up to here, right? So I strongly recommend when you're doing energy problems to label states. Say like this is point A, and this is point B, and that's point C. That'll help you think of them as different states. Oh, that was an old question. Okay. And since we're doing gravity kind of problems, there's going to be potential energy involved. You got to define where 0 is. That's another good thing to do at the beginning. Where is 0? Well, we'll say 0 is going through the center of mass of this ball. That's the lowest anything went, so we'll call that y equals 0. And we'll say at that position, ug equals 0. So we're saying, okay, we agree the bottom is where there's no potential energy. That way, everything that goes higher, we can just call it ugy, right, as we go up in the y position like that. Right? Okay, so now we're all set up. And then the height would be like this. There's that height h. Let's see, release from h. So when you released it, it was a height h above the bottom, like that. That's a little messy. Okay. So now the question was, how fast is it at the bottom? So we go from A to B is the question. So A to B. So all we're doing is we're saying this thing, we're going to release it up to some height like this. Don't anybody get up. Right? It's higher, and we let it go. How fast is it going at the bottom? Right? That's all we're saying. So let's see if we can figure that out. As an energy problem, there's an elementary energy problem here. I wanted to do it. I decided let's use initial final. Right? So Ki plus Ui. I'm going to leave off my G's because we're only doing gravitational. Kf plus Uf. Right? So let's see if you think you could fill out all 4 of those numbers. Let's see. I wrote it backwards. Ki, what's the initial? Like release from H. It's almost always implied when you release something, it's also from rest. The full problem hopefully would have said that. Right? You release something, you're holding it still, and you release it and something happens. So Ki is 0. Right? V is 0 at the beginning. Ki is 1/2 mv squared. V is 0, so K is 0. The initial the initial potential energy is mgy and y equals h. Right? So it's mgh. So we're not going to redrive all that in the work. We're just going to say, from the last lecture, we know it's mgy, and now y equals h. Final. Then you got to be able to realize this is what we're looking for. This is where your answer is hiding. Right? You say, what's the final? 1/2 mv. I don't know, v final. Oh, that's what I'm looking for. Okay, yeah. So if you ever say, I don't know this, that might be the answer. And then what is the potential energy final? 0, right? We define that to be 0. Remember? Right, so there you go. So by setting it up that way, you can turn it around and say, oh, the mass doesn't matter. Look at that. And you can say the 2 comes over here, and you see that V final equals the square root of 2gh. Okay. Squared to, V final squared root of 2gh. So that is the formal way to do that problem, where you write down the law of conservation of energy. If you have an intuition for this, you can say, oh, well, yeah, mgh equals 1/2 mv squared. Right, you don't have to write all that down every time if you don't want. But if you're not sure what to do, go to one of those 2 equations. Okay? Usually, once you get an intuition for it, you hardly ever write those down. You just say, oh, I see some energy here, it went here. But you shouldn't be able to do that now. It's okay if you can't do that now. Let's also ask a second question. What if we go from B to C? How high does it get? All right? What level is it going to get up to? B to C, well, now we would say, let's apply the same thing. Now everything is different. Initial plus final. Now initially it has this much Ki, 1/2 m, the square root of 2gh squared. Right? We solve this part. It's going that fast when it's down here. So that's the initial kinetic. What's the initial potential? Now the initial potential is 0, right? Because we defined it to be 0. Well, what's the final kinetic going to be? 0. That's again where you have to interpret the problem. How high did it get? What happens when it gets to its maximum height? It stops. Okay? So that would be an intuition to gain about pendulums, is that that's 0. Because how high means it came to a stop, plus mg, and I'll call it h2. Right? How high does it get over here? Right, h2. And you can probably see we're just sort of going in a circle here. Right? So you square this, so it's really just 2gh, and that cancels that. And then that cancels that, and that cancels that. And you see h2 equals h. It goes to the same height. Right? If you started with some potential energy here at h, it gets converted all to kinetic. And if you're going to lose all that kinetic, you got to go to the same height as the original. All right? So we will do harder problems in your homework, and in class we'll do harder problems. But that's the very basic idea of how to use this. Now this is something, does everybody believe that it will go to the same height? Are there any non-believers in here that need to see it proven to you? Right? This is the big famous thing that you do, right? If you know it's going to go to the same height, and you're brave, and you really believe it, you hold it up to your face and release it. Oh, yes, we bring this over here. And when the room is big enough and the bowling ball is big enough that you grab it and you come over here. Oh, whoops. How do I do this? Is this thing shorter than usual? All right. And you stand back here. You got to be all the way back. I think my arm got shorter. Oh, no, I had this going this way. Oh, wow, if I drop this, somebody could get hit. Okay. Okay, don't anybody get up, right? So the thing you do is you release it from here, and then it goes forward, and if it comes to the same height, it won't hit me in the face, right? Has anybody, y'all seen this before, right? You've seen this on YouTube? Well, there's really no dramatic tension then if you've seen it before. And also, like, if a physicist gets hit in the face and gets messed up, I mean, it doesn't really matter. So what I'm going to do is I'm going to raise the stakes, or you might say I'm going to lower them, okay? You've never seen this on YouTube before, okay? So I can't back up. I'm stuck right here. Are you ready? So I call this the Hafner's pendulum, or no, I forgot what I call it. Yes. Oh, okay. Okay, so you've never seen that on YouTube, and I don't want to see it on YouTube. Okay, so we'll do our break, and we'll do a 5-minute break.